100 facts about capacitors. Basic concepts. 1. A capacitor is a passive electronic component that stores electrical energy in an electric field. 2. It consists of two conductive plates separated by an insulating material called a dielectric. 3. The unit of capacitance is the farad, F. 4. Capacitors can be classified based on their dielectric material, such as ceramic, electrolytic, paper, mica, and film. 5. The capacitance of a capacitor depends on the area of the plates, the distance between them, and the dielectric constant of the material. 6. Capacitors can be connected in series or parallel. 7. When capacitors are connected in series, their equivalent capacitance decreases. 8. When capacitors are connected in parallel, their equivalent capacitance increases. Capacitor applications. 9. Capacitors are widely used in various electronic circuits. 10. They are used to smooth out voltage fluctuations in power supplies. 11. Capacitors are used in timing circuits, such as oscillators and timers. 12. They are used in filters to block or pass certain frequencies of signals. 13. Capacitors are used in energy storage applications, such as flash photography and defibrillators. 14. They are used in coupling circuits to isolate different stages of amplifiers. 15. Capacitors are used in resonance circuits to tune radio receivers. 16. They are used in power factor correction to improve the efficiency of electrical systems. 17. Capacitors are used in motor starting circuits to provide a surge of current. 18. They are used in sensor applications to measure changes in capacitance. 19. Capacitors are used in touchscreens to detect the location of a finger. 20. They are used in RFID, radio frequency identification, systems to store and retrieve data. Capacitor characteristics. 21. Capacitors have a capacitance value, which determines their ability to store charge. 22. Capacitors have a voltage rating, which indicates the maximum voltage they can withstand without breaking down. 23. Capacitors have a leakage current, which is a small current that flows through the dielectric. 24. Capacitors have a dielectric absorption, which is the ability of the dielectric to retain a charge after being discharged. 25. Capacitors have a temperature coefficient, which indicates how their capacitance changes with temperature. 26. Capacitors have a frequency response, which describes how their capacitance varies with frequency. 27. Capacitors can be polarized or non-polarized. 28. Polarized capacitors have a positive and a negative terminal, and must be connected correctly to avoid damage. 29. Non-polarized capacitors can be connected in either direction. 30. Capacitors can be fixed or variable. Capacitor history and theory. 31. The first capacitors were Leyden jars, invented in the 18th century. 32. The theory of capacitors was developed by Benjamin Franklin and Michael Faraday. 33. Capacitors are based on the concept of electric field lines. 34. The electric field between the plates of a capacitor stores energy. 35. The capacitance of a capacitor is directly proportional to the area of the plates and inversely proportional to the distance between them. 36. The capacitance of a capacitor is also affected by the dielectric constant of the material between the plates. 37. The dielectric constant is a measure of the ability of a material to store electric energy. 38. Different materials have different dielectric constants. 39. The dielectric constant of a vacuum is 1. 40. The dielectric constant of air is approximately 1.006. Capacitor safety. 41. Capacitors can store a significant amount of energy, even after being disconnected from the power source. 42. It is important to discharge capacitors before handling them to avoid electric shock. 43. Capacitors can be discharged using a resistor or a short circuit. 44. When working with capacitors, it is important to use appropriate safety precautions, such as wearing gloves and using insulated tools. 45. Capacitors can be damaged if they are subjected to excessive voltage or current. 46. Capacitors can also be damaged if they are heated to excessive temperatures. 47. Capacitors can be damaged if they are exposed to moisture or corrosive substances. 48. It is important to store capacitors in a dry, cool place to prevent damage. Capacitor types. 49. Ceramic capacitors are made from a ceramic dielectric. 50. Ceramic capacitors are available in a wide range of capacitance values and voltage ratings. 51. Ceramic capacitors are often used in high-frequency applications. 52. Electrolytic capacitors are made from a metal oxide dielectric. 53. Electrolytic capacitors have a high capacitance value for their size. 54. Electrolytic capacitors are often used in power supply applications. 55. Paper capacitors are made from a paper dielectric impregnated with oil or wax. 56. Paper capacitors have a moderate capacitance value and voltage rating. 57. Paper capacitors are often used in audio and power supply applications. 58. Mica capacitors are made from a mica dielectric. 59. Mica capacitors have a high capacitance value and voltage rating. 60. Mica capacitors are often used in high-frequency applications. Capacitor types, continued. 61. Film capacitors are made from a plastic film dielectric. 62. Film capacitors are available in a wide range of capacitance values and voltage ratings. 63. Film capacitors are often used in audio and power supply applications. 64. Variable capacitors have adjustable capacitance. 65. Variable capacitors are often used in tuning circuits. 66. Trim capacitors have a small capacitance value and are used for fine adjustments. 67. Supercapacitors have a very high capacitance value and can store a large amount of energy. 68. Supercapacitors are often used in energy storage applications. 69. Double-layer capacitors, EDLCs, are a type of supercapacitor that uses a carbon-based electrode material. 70. EDLCs have a high power density and can be charged and discharged quickly. Capacitor theory and calculations. 71. The capacitance of a parallel plate capacitor is given by the formula C equals epsilon A, D, where C is the capacitance, epsilon is the permittivity of the dielectric, A is the area of the plates, and D is the distance between the plates. 72. The capacitance of a cylindrical capacitor is given by the formula C equals 2PL, lane, B, A, where C is the capacitance, epsilon is the permittivity of the dielectric, L is the length of the capacitor, and then B are the radii of the inner and outer conductors. 73. The capacitance of a spherical capacitor is given by the formula C equals 4P BA, where C is the capacitance, epsilon is the permittivity of the dielectric, and B are the radii of the inner and outer conductors. 74. The equivalent capacitance of capacitors in series is given by the formula 1, CEQ equals 1, C1 plus 1, C2 plus 1, Cn. 75. The equivalent capacitance of capacitors in parallel is given by the formula CEQ equals C1 plus C2 plus Cn. 76. The energy stored in a capacitor is given by the formula U equals 1/2 CV squared, where U is the energy, C is the capacitance, and V is the voltage across the capacitor. 77. The power dissipated in a capacitor is given by the formula P equals IV, where P is the power, I is the current flowing through the capacitor, and V is the voltage across the capacitor. 78. The time constant of a capacitor resistor circuit is given by the formula tau equals RC, where tau is the time constant, R is the resistance, and C is the capacitance. 79. The voltage across a capacitor in a series RC circuit is given by the formula V, T, equals V0 E caret, T, tau, where V, T, is the voltage at time T, V0 is the initial voltage, and tau is the time constant. 80. The current flowing through a capacitor in a series RC circuit is given by the formula I, T, equals V0, R, E caret, T, tau, where I, T, is the current at time T, V0 is the initial voltage, R is the resistance, and tau is the time constant. Capacitor applications, continued. 81. Capacitors are used in audio amplifiers to couple different stages of the amplifier. 82. Capacitors are used in power factor correction circuits to improve the efficiency of electrical systems. 83. Capacitors are used in motor starting circuits to provide a surge of current. 84. Capacitors are used in sensor applications to measure changes in capacitance. 85. Capacitors are used in touchscreens to detect the location of a finger. 86. Capacitors are used in RFID, radio frequency identification, systems to store and retrieve data. 87. Capacitors are used in medical devices, such as defibrillators and pacemakers. 88. Capacitors are used in automotive electronics, such as engine control units and airbag systems. 89. Capacitors are used in renewable energy systems, such as solar panels and wind turbines. 90. Capacitors are used in telecommunications systems, such as modems and routers. Capacitor troubleshooting. 91. If a capacitor is faulty, it may exhibit symptoms such as bulging, leaking, or discoloration. Capacitor troubleshooting, continued. 92. If a capacitor is faulty, it may cause the circuit to malfunction or fail to operate properly. 93. To troubleshoot a capacitor, it is often necessary to measure its capacitance using a capacitance meter. 94. If the measured capacitance is significantly different from the specified value, the capacitor may be faulty. 95. If a capacitor is suspected of being faulty, it can be replaced with a new one of the same type and value. 96. When replacing a capacitor, it is important to ensure that the polarity is correct, if applicable. 97. Capacitors can be tested using a multimeter to measure their leakage current. 98. If the leakage current is too high, the capacitor may be faulty. 99. Capacitors can also be tested using an oscilloscope to observe their voltage waveform. 100. If the voltage waveform is distorted or irregular, the capacitor may be faulty.